It can be challenging at times because GaN switches so quickly that it makes measurements somewhat difficult. In addition, trying to get a good measurement of a high side gate signal, for example, can be quite challenging. So I'm going to cover some of the techniques that we use to help us get reliable measurements in the lab. So I'm going to talk about the double pulse test technique that you can use to make sure everything is functional before you apply full power. I'm going to talk about the bandwidth of the probes and the oscilloscope system that you need in order to be able to accurately measure. We'll talk about measuring the low side gate source voltage on GaN, how to measure the drain source voltage, and then also the high side VGS, which is quite challenging. In addition, we'll talk about isolated probes, what types to use, because there are several different types out there. And we'll talk about the differential mode probes and the common mode transient immunity, which is a measure of how well they can measure a small signal riding on top of a bunch of noise, and then we'll summarize. So I mentioned this double pulse technique. When we evaluate power transistors in our lab, we often use this technique called double pulse in order to exercise the power transistor through its entire range of voltage and current and see how it behaves in switching and so on. The same kind of technique is helpful when you first power up a circuit because you don't know that everything is working properly. Maybe it's not best to start by trusting your controller and software are all working perfectly. So you can either use an external signal generator to do this, or you can write a small piece of software to trigger the appropriate switching behavior using the controller. So the idea is this. Here's the circuit. Usually these are half bridges. Q1 is high side, Q2 is low side, and you have some sort of an inductive load. The double pulse, the most common is the low side, which means that this Q2 is going to be my switching transistor, and Q1 is really just operated as a diode, so I can leave it strapped off. Then I connect the inductive load to the positive rail. So the idea is when I turn on Q2, I establish current flowing this way. And I don't have to do this with full bus voltage. I can start with a 10 or 20 volt bus in case there's a problem, then I don't blow everything up. I just can, see that the current is higher than I expect. Set your power supply current limit to something safe. So I get current flowing in the inductor, and then when I shut off Q2, now the current recirculates here through Q1 in the opposite direction. So it's just a freewheeling diode. And I can do this several times. So first, just make sure everything's switching the way you expect and that all the timing is correct and the signals work properly. Then you can bring up the full bus voltage, and by turning on Q2, the first pulse here, pulse 1, I ramp it up to some current. Then I shut off Q2, and I don't even need to turn on Q1 here. I can just leave it in diode mode if I want. I can just leave Q1 off completely the whole time if that's simpler to implement on your system. In any case, each pulse of Q2 will ramp up current to some value, and then it holds. It's very slightly dropping off like this, but during a relatively short hold period, I can then let the system settle out and give it another pulse for the next measurement. This is how the intent is. It doesn't have to be just 2 pulses. You can set it up for incrementing up from 1 amp up to 10 or 20 or 50 or whatever you need. And this is what you should expect to see on the right-hand side here. So if I look at, for example, my low side gates, this would be Q2. Here is turning on, turning off. And then similarly, you can see the high side, a short dead time, high side turns on, high side turns off. This is the voltage. You would see then VDS, so that's the switch node voltage from right here. And you can see the inductor current is measured with a current probe here. This is at 5 amps per division, so 5, 10, so this is 15 amps, then on up to 30 amps. Everything looks good. There's nothing unexpected. That's what we're hoping to see. So the next question is, what kind of bandwidth do I need? maybe my converter is only running at 50 kilohertz. So if I, for example, use a 100 megahertz scope, that should be way more than enough, right, to handle a 50 kilohertz switching waveform. But the answer is no. Actually, the bandwidth you need in the scope has nothing to do with the PWM frequency. It's all about the edge rate. You know, the PWM frequency just refers to how frequently these edges occur. And what really is important is the rise and fall time. That determines the overall spectral content of this waveform. A signal can be relatively low frequency, like 50 kilohertz, for example, but it has very wide bandwidth due to the fast edges. You can approximate this. The kind of a rule of thumb here is that if I know the rise time of the signal, like for example, here is one that's going from 0 to 400 volts in about 3.5 nanoseconds, not uncommon for a fast GaN transistor. I'll skip the math here and just get straight to the point. Bandwidth that you need, that's present in this signal, is 0.35 divided by the rise time. So in this example, 0.35 over 3.5 nanoseconds, that's 100 megahertz. Now, if I'm measuring this signal on a 100 megahertz scope, I have to ask the question, is it the scope that's limiting my rise time? Is that what I'm seeing as the limit of the scope? Maybe it's even faster on my real circuit. Really, I believe you need 500 megahertz, and even up, even a gigahertz for very fast switching GaN devices. I have seen examples of oscillations near a gigahertz, where a 200 megahertz scope just shows a weird waveform, but it's all filtered out. Now I go to a gigahertz scope and I can see the oscillation. That's how fast and how wide bandwidth GaN is. You'll actually see 800 or 900 megahertz oscillation when things go bad. The lesson here is don't use a 100 megahertz scope. 200 is barely adequate. I've seen gate ringing signals at 400 megahertz. So 500 megahertz is the minimum. I'd recommend a 1 gigahertz scope. And that includes the probes that go with it. So speaking of probes and measurements, there are a number of different points you need to look at. And I think it's really important that when you first power up a system, don't just say, it seems to be working, the output looks good, so I'm going to assume the gate is okay. Don't trust that, measure it. You need to take a look and see, is it fully on? Is it barely on? Is there noise, ringing, whatever? You need to look at the gate signal. So I've shown in this diagram here a couple of points that you should look at when you're looking at the system for the first time. One is on the low side gate. Then there is the switch node in the middle of the half bridge. And then there's the high side gate. And let's talk about how to make these measurements and what probes to use and how they work. So let's start on the low side, just the simple gate source voltage. Usually your scope is going to be connected to this low side ground anyway. Now on some transistors you have two source terminals. There's the power source terminal, and then there's what's called the Kelvin source, which is connected to the gate drive circuit. So if I want to measure the gate drive circuit, my probe ground has to go to that point, which might not be exactly ground. And this is where some of the probe techniques come in. Let me show you one way that you can use to help get the highest integrity signal on the gate. So this is a standard 10x probe that you get with a scope. This one is 500 megahertz bandwidth. And you've all seen the typical leads that come with these probes. Some of them come with long wire leads that you absolutely don't want to use. What I want is on the probe tip that I have as short of a loop area here as possible. I want a very short lead, and there are even little spring clip leads you can put on here to get a really tight connection. And then this is my source, that'll be my gate. But as I mentioned, if this isn't ground and the scope is at ground, now I'm going to have potentially currents flowing through my cable that I didn't intend, right? It'll be like a ground loop current. So one way to mitigate that is you put, I've shown in the example here, this is a ferrite common mode core around the cable. You can even put a couple of turns on it to get extra impedance. What this does is it allows the probing end to move up and down a little bit with the circuit without creating currents, because this core makes a high impedance in the cable shield at high frequency. Another way you can do that if you don't have these kind of clip-on cores is you can just use a large ferrite core like this, and you can put the probe through it, a couple of turns like this, and there you go. You can now use this without worrying about common mode currents in the probe shield. There's a second way to measure the low side signal if you have common mode voltage problems, and that is using a high common mode differential probe. So this one it's a low voltage. It's not meant to go to the high side. The common mode range here is like 40 volts, which is good enough that I can put whatever tip I need on here, get this, the probe tip onto my circuit board, and I can now make reliable differential measurements right on the circuit board without the interference of common mode noise. This is an active low voltage differential probe. There are many companies that make this. Usually each scope brand has their own version of it. If you're using LaCroix, if you're using Tektronix or whoever, you get usually the one that goes with that scope. Okay, for measuring the switch node voltage, it's a little less critical. I mean, it's a big signal, so you've got hundreds of volts here. The important thing is some of these probes, like for example, if I look at the one we were just looking at, it's a 400 volt probe. If I have a 400 volt bus, do I want to use a 400 volt probe? It's kind of sketchy, kind of pushing it. Maybe I want something a little bit higher. Some of them are only rated at 300 volts. So you really should use a probe here that's high voltage. There are some in the range of like 1 kV, 1.5 kV that still have really good bandwidth. They're no longer a 10x probe. They're usually like a 50x probe, usually 800 megahertz or so bandwidth, and they work very well here. And again, remember that this ground on the probe is going to connect to the circuit ground. So if I have one probe, passive probe here connected to circuit ground, and I have another one connected to Kelvin source, it's just another reason why you want to use that common mode core. I just put the common mode cores on every probe that goes to the scope, and that solves a lot of noise problems. Now let's talk about measuring the high side gate, because this is really difficult. I'm essentially trying to measure a couple of volt signals riding on top of a 400 volt fast square wave, right? Probably with ringing and overshoot on it. So I need to only measure the differential portion here and ignore that whole common mode voltage. There are probes, so I'm going to show you again a couple of probes. So this one here is made again by multiple different vendors, each one for their own scope brand. This is called a high voltage differential probe. It has a pretty high bandwidth. This one is like 400 megahertz. The challenge is that that's the bandwidth under ideal conditions, and assuming there's no big common mode transient. What happens is that if I try to connect these giant clip leads, I've got a circuit that has little tiny 402 resistors on it, right? These are just too big to work with. And moreover, when I do get it clipped on, I've got a great big search loop here, an antenna, a coil with susceptibility. It's going to pick up the stray field from your PFC inductor or whatever, any magnetic field nearby is going to induce voltage into this because it's not shielded, it's not even twisted pair. I mean, you can try to do something to make it better, but really this is not intended for the kind of measurement I'm talking about. This is intended for measuring maybe thyristor signals on a 60 hertz waveform or something like that. The issue is it doesn't have the common mode transient immunity necessary to give you an accurate signal. I'll show you some examples of what happens when you use one of these instead of the probe I'm about to show you. So these are very good probes when they're used for the correct purpose, but these are not intended for really high common mode transient immunity. To do that, really the only way to accurately measure the high side gate is with a fully optically isolated probe. This is, again, an example. This is a Teledyne LaCroix. They're made by Tektronix. There are also third-party vendors that make these. Each one typically has a couple of elements on it. There's these removable probe tips that have attenuators on them. So this one, for example, is for 200 volt peak to peak. If I'm measuring gate voltage signal, I'd probably be using a 20 volt peak to peak probe. And it has a coaxial connector on the tip. So this whole thing is shielded, and it connects to a little tiny MMCX connector that's on your PC board to keep everything shielded. And the real key is that this whole preamplifier box is connected with a fiber optic cable. So this cable that connects then to the base unit is fully fiber optic. So there's absolutely no electrical connection on this. The power is provided by a laser diode that powers this, and then it sends back an optically modulated signal. The good news is that it has incredible common mode transient immunity. I'll show you that in a minute. The bad news is one of these costs probably about as much as the entire scope. They range from $15,000 to $25,000 a piece. So if you need a couple channels of it, it's a big investment. But there's nothing else to compare with an optically isolated probe like this. This one has a 1 gigahertz bandwidth also. So let me show you how to analyze or look at these probes. Oftentimes these probes give you charts that list, it's like an Excel table here of at various frequencies, what's my common mode rejection ratio? My question is, if I hook this up onto my gate drive circuit and I know I have a 400 volt common mode transient at 5 nanoseconds wide, how much error voltage am I going to see on my measured differential signal? I have no idea with this kind of data, right? I mean, I understand why they do this. This is the way that they're able to measure common mode rejection ratio. This is how it's done in the RF world. But I have a bunch of different frequencies, spectra going on, and I can't sum this up and make sense of it. So what I really want to know is, what's the error voltage? And I'm not going to get that answer because it depends on my circuit and my setup. So I should measure it myself, and that's exactly what I do. So the way you do that is you set up this probe just like you're going to measure with it, only you short the signal and ground together. So you need to have your board pre-set up to be able to do this, but this enables you to essentially make the whole probe, it's switching up and down with your signal, but the differential signal is 0, and that means you should see 0 on your scope. So here's an example. You can see the switch node. This is a really fast transient here. This is at 10 nanoseconds per division. So, rise time and overshoot here. And I have 2 of these optical probes, and they're both set at 2 volts per division, which is what I would be using to measure my gate signal. And ideally, it would be absolutely flat, 0. You can see I do have a little bit of anomaly here, but, compared to what you're about to see from the other kinds of probes, this is quite good. This is about as good as you can get today. I've never seen a probe, nothing's perfect, right? So the common mode transient signal is attenuated. If I say I'm going from 400 volts, 0 to peak, down to 1.5 volts, 0 to peak, that's, almost 50 dB of attenuation, which is quite good. As long as I know what this looks like, now I can subtract this from my true measurement. On the other hand, if I try to use one of the other high voltage differential probes that I showed earlier, here's what you get. Same test, right? I expect 0 here, but you can see I've got 2, 4, 5, or 6 volts and a whole bunch of noise and then settling out going on. That's what I mean when I say that the high voltage differential probe, it's a differential amplifier that's trying to ignore the common mode voltage and only look at the differential. And it does a good job considering, its capability, but it's just no match for the optically isolated probe. If you use one of these, it's really not, you can't trust the result. I don't know what my gate signal really looks like when I have 6, 8, 10, 12 volts peak to peak of noise, right? I can't make any judgment on this. I mentioned that passive probes, they can be affected by common mode currents. This is just an illustration to show that and to understand where does that current come from. The signal of interest here, if this is my signal generator, this is my circuit I'm measuring, and this is my coaxial cable going to my scope, I have inside of the coaxial cable of the probe, I have completely matching and balancing current. So this gives me that shielding effect, and essentially everything outside of the cable is ignored. All of the electric and magnetic fields are contained inside the cable. But when this whole circuit is moving up and down, I have capacitive current through earth back to the scope. Now, where does that return? Through my shield of my cable. That's what I mean. When I have different potentials on either end of the probe, I have an unseen return path, which is through earth. That's the common mode current. And when I get that in my probe shield, it unbalances these signals, so I now inject noise into my probe, which is supposed to be shielded. That's why by adding the common mode core across this, it makes this a high impedance path and eliminates that common mode current. In conclusion here, we talked about how to accurately measure the high side gate signals. That's particularly challenging, especially when we've got slew rates of 50 to 100 volts per nanosecond. That's the common mode signal we're trying to reject. There are different probe types available. The low-cost ones are not isolated. They're high voltage differential amplifiers. As I said, they're fine for their intended purpose. This is not one of them. You really need the optically isolated probes. It's a big investment. You can rent them, of course, but it's necessary to at least validate and verify that your gate signals are doing what you expect on your GaN circuit. The differential probes typically don't even have sufficient bandwidth. The one I showed you is pretty good, 400 megahertz, but some of them are only 100, 150. The differential probes also don't have common mode DVDT, immunity or rejection. So you end up with these error signals that are larger than the signal you're trying to measure. I hope that's helpful. Check out the other videos in this series on the Infineon website that talk about other aspects of designing with GaN power transistors.